All right, thank you. Great lineup of talks here, and I hope to follow up on the previous discussion with my talk. So I'm going to be talking about work I'm doing for my PhD dissertation, and it's looking at changing glacio-hydrologic patterns across the Pacific Northwest. So I want to start off by acknowledging people involved in this research, starting with my advisors here at UW and a host of other individuals in organizations across the Pacific Northwest who have provided both glaciological, climate, meteorological data for these analysis, but also their expertise from years of experience on this topic. And finally, I want to acknowledge funding sources being NASA and Seattle City Light. So as we noted with the previous talks, glaciers are a critical component of the water resources in the Northwest as they contribute to summertime low flows. Their importance is further enhanced during drought years as there's limited inputs from snowpack, and the glaciers are more exposed, so they're able to modulate and buffer low flows across the region. And if you look at some of the water management infrastructure in the region, they're nested right below these partially glaciarized catchments, starting with the Puget Sound Energy Project below the Mount Baker, Seattle City Light in the Upper Skagit, North Cascades, 3 hydroelectric power facilities that give most of the energy to the city of Seattle. Tacoma Power operates Alder Dam just below the south side of Mount Rainier. And it's not just dams. I am an engineer, so I love my dams, but it's also, glaciers are important for in-stream flows for fish and also agricultural water supply. An example of that being the Hood River Basin shown here, where glacier-fed rivers supply irrigation water for the orchards and vineyards in the lower basin. So how are these partially glaciarized watersheds going to change with glacier recession? How is the stream flow variability going to change? And this can be thought of in 4 distinct conceptual phases. So at the onset of warming, you get this enhanced rate of melting of the glaciers. This leads to increased discharge from these watersheds. In the meantime, the glaciers will start to recede and lose area, and they'll recede to a point where the area has reduced enough that it no longer matters that it's warmer and things are melting at a faster rate. The area is reduced after which you'll start to see declines in watershed discharge. So the second phase is often referred to as peak water. So moving beyond this peak, where the glaciers will continue to recede, they're still melting fast, but the air is small enough that you'll see continuous declines in watershed discharge. And the glaciers will eventually recede to a point where they're no longer key contributors to watershed discharge. So for watersheds with glaciers in them, understanding these different phases is really paramount for long-term water resource management. So understanding what phase is currently being experienced and the timescales and arrivals of subsequent phases. So to look across the region at these changing processes, we've selected 8 different watersheds to analyze and compare to capture what has happened and what may likely happen with continued climate warming. We've selected watersheds that are important to local water management, but more importantly, we've chosen watersheds that have both records of glaciological as well as hydrological measurements to analyze and use in hydrologic modeling. We've also selected watersheds with different environmental attributes so we can compare and understand why some areas are responding differently than other areas. Now, zooming in on a few of these watersheds, here I'm showing 3 in the North Cascade, the Thunder Creek watershed, the Cascade River, and the Stehekin River Basin, and also the Nisqually River Basin just south of Mount Rainier, which drains to that Tacoma Power facility. Looking at the relative change in these areas, in the North Cascades, I only have 1950 to 2010 glacier areas shown, but depending on the watershed, it's about 6 to 10% change in glacier area. The latter part of the last century, there was less change in the earlier part. And as you can see in Mount Rainier, it's about a 20% reduction, and that is comparing 1913 to 2009. And most of this extent data is from Andrew Fountain's group. down in Portland. So we've selected these watersheds because there's local measurements available. However, these local measurements do not necessarily allow us to look at long-term changes due to their length of record. So to supplement the measurements and to use the we use a hydrologic modeling approach. So we're using a coupled glacial hydrologic model. This is the DHSVM, Distributed Hydrology Soil Vegetation Model. Recently incorporated into this model is a representation of glacier dynamics, so the dynamic downslope flow of ice. And this is essential for the prediction of long-term forecasts of low flows, because you need to accurately evolve the glacier area based on changes in accumulation and ablation that are occurring on the surface. Now, there's a lot of details on this modeling approach shown here. I'm not going to go into any of them, but feel free to pull me aside and ask me if you're more interested in the modeling methodology. So I was highlighting the importance of having glaciological measurements. If you weren't sure, you need to ensure that your model can capture the fluctuations in glacier mass and area to have any confidence in the model predictions for the future. An example of showing of how the model is able to reproduce glacier mass is comparisons for South Cascade Glacier and the Blue Glacier on the Olympics. We're still working to improve the simulation for Blue Glacier. However, the model is fairly accurately representing the changes in mass on the South Cascade Glacier. And this is comparing the annual net balance, so the amount of ice and snow that's either lost or gained on the glaciers in a given year, expressed in meters water equivalent. We also want to make sure that we're capturing the aerial change, the trajectory of aerial change of the glaciers. So on the bottom here, I'm showing examples of simulations on Mount Hood with the simulated ice water equivalent, the ice volume shown in purpley blue colors, and estimates of the ice extent shown with the black lines. We need to make sure that we're able to capture fluctuations in mass and area in order to do this type of modeling. I'm going to walk through a model application to show how we can use this analysis to describe an individual watershed and then make comparisons between these watersheds. So I'm going to show you simulations for the Hood River in Oregon. Like I had mentioned earlier, the glacier melt here is important for irrigated water supply, as there's orchards and vineyards, perennial crops that need access to irrigated water during the summer every year. And the glaciers are important here, even though the glacier cover is relatively modest, because the locations where they're diverting water for water supply are at high elevations on these glacier-fed streams. I'm going to talk about one in particular. This is the Elliott Creek diversion location. So all of the results I'm going to show are for this water management location. So historically, here is from 1916 to 2010. This is model simulated total discharge at this location, shown in blue per day of year over this period. Now the glacier melt component of that discharge, the mean per day of year, is shown in black. And when I say glacier melt, it's the melting of glacier ice only, doesn't include snow or rain falling on the glacier. Now the maximum glacier melt discharge per day of year is shown in red. So on average, the contribution of glaciers in September is about 50%. The maximum contribution in a given year is about 50%. However, it can be up to about 80% in the most extreme years when the glaciers are least covered in snow and there's little input from other sources, so years of drought. Looking at a time series of this data, so this is September discharge volumes. The total discharge is shown in blue. The snow and rain component of that discharge is shown in red, where the black line shows the component that's coming just from glacier melt. The solid lines are the 10-year running means. So you see some interesting patterns in years where you have a lot of snow melt contribution. The glaciers don't contribute very much because they're covered in snow. But more importantly, when you don't have that snow melt contribution, the glacier melt increases. So your overall variability in total discharge at this water management location is fairly low due to this ability of the glaciers to modulate the stream flow. Now, in the more recent years, you see a continuous decline in the snowmelt-related discharge, a slight increase in the glacier melt component, which is reflected in the relatively modest change in total discharge. So how are these going to change into the future? We don't really see a clear pattern of response like I showed you on the conceptual diagram. So to look at a longer record, we run future simulations, and these are using the downscale data from 10 different GCMs for 2 emission pathway scenarios as part of the integrated scenarios project. Shown here is the predicted progression of glacier area for the Hood River. The dark lines are the mean of the 10 GCMs, whereas the lighter lines are predictions of individual GCMs. So in the more, the optimistic case is a near linear decrease in glacier area continued through the century, whereas the, as said earlier, the business as usual case, it starts to dive off much more quickly later in the century. So how is this changes in glacier area going to translate to changes in discharge at this location? Again, this is the Elliott Creek location, and I'm only showing September discharge volumes, the time of the year where the glaciers have the strongest signature. So in the near future, we see a decrease in this non-glacier related discharge, largely due to changes in snowmelt, where we're seeing an increase in the glacier melt. So not much change in the total water availability, but later in the century, we do see declines in glacier melt due to a reduction in glacier area, and this is expressed in the total water availability at this location. So this is an example of how we can use this modeling approach, constrained with all the observational data that's available, to really describe what's occurring and what could possibly occur with future warming. So where we're going with this is to have these simulations in 8 of these different watersheds, and then we'll be able to diagnose what phase of hydrologic response is being experienced, and be able to show them on a plot like this and really capture what's going on across the Northwest. Furthermore, we want to look into the future and predict what is likely going to be the phase at different slices in time for each of these watersheds. And to look at each watershed as an individual in terms of these phases is important for water management. However, compositing the watersheds based on their environmental attributes may allow us to understand more the mechanisms and the sensitivities of why certain areas are changing and others aren't. Finally, if we can generalize the pathway of hydrologic response based on these different watershed environmental attributes, we can understand the changes more readily. For example, if watershed is the glaciers are debris covered, we may see a much slower, less pronounced response of these phases. Southern aspects may be more sensitive, and so on and so forth with these different watershed characteristics. So I provided a framework for understanding this glacio-hydrologic change across the Northwest. I've shown you one example which indicates in the Hood River Basin at this water management location that glacier melt is going to continue to increase until about mid-century, compensating for losses in snowmelt-derived runoff. However, later in the century, the glacier melt will decline with the declining glacier area. So ongoing data analysis and model applications that I'm running for these 8 different watersheds will allow us to get a better picture of what's occurring, what's likely to occur, and kind of the time and spatial scales at which glacier melt is important for our management of water resources.
Great work, Chris, and you stayed ahead of schedule, so you didn't really David.
David Roop, Oregon State University. Nice talk, Chris. Do you have, and maybe I missed this, but do you have any observations that confirm that when you're getting more runoff from snow and rain, you're getting less from the glaciers? It's an interesting signal, and it affects what the projections are for the next 10, 20 years down the road. Excuse me.
No, we don't have any direct observations to validate that. We do have. So. Certainly, separating snow and ice chemically is difficult. So typically, isotopic studies that separate glacier melt from non-glacier melt include snow, because they're taking a sample right at the snout of the glacier. So it's harder to find a distinct chemical signature between snow and if you look at stake measurements, you can you get a better handle of whether it's melting snow, like whether you can physically measure whether it's snow or ice, and then extrapolate that, and that's been done, and John's been able to do that to separate whether it's snow or glacier ice as the contributor.
While he's hiking, I'll introduce Guillaume Mauger, University of Washington.
Thanks. Nice talk. I sort of a follow-up question to what David was asking. It seems like you might be able to use the historical record to do some of the sensitivity testing you're talking about doing with the projections. You know, we have variability, and could you sample the natural variability and look at the responses in the glaciers that are associated with warmer years or decades and cooler years or decades to get at some of the questions you're asking?
Is there a question?
I don't know if that's feasible.
Do the historical sensitivity of.
Yeah, and if that's something that you're doing.
Well, it's difficult because the area is going to be constantly changing. So you have to. So if you look at a warm period in 1950, it's going to be different than the same warm period now because it's going to be a different area. So I think it would be possible, but we'd have to think about how it would be done in more.
This is Asim Sarma from University of Northern British Columbia. I have a quick question. On your presentation, maybe I missed the point. You say about mostly the rainfall-dominated runoff will be occurring in the future, but do you think there will be increased runoff in future or decreased runoff in future? Generally, like with warming, it is expected that there will be increased precipitation in the form of more the rainfall than snowfall. So do you think it's more increase will be the in runoff or decrease in the runoff?
Well, I'm largely dealing with so late summer runoff. So it's going to be attributed to how much snow is able to accumulate. So when I'm showing the decreasing in the red line, there can still be increases in precipitation, but it may not fall as snow. So you can the temperature influence will end up reducing that late summer flow.
So total river runoff will be almost the same then?
So at the annual scale or just dry season?
Annual scale, I mean.
The annual scale, it may be the same, but dry season will be more effective as you're looking at your timing